Hello, everyone. My project was titled Catecholamine Derivatives as Modulators of MMP Activity. So for some introduction, matrix metalloproteinases, or MMPs for short, are a family of proteolytic enzymes primarily responsible for the remodeling and degradation of the proteins comprising the extracellular matrix, which is a network of proteins and carbohydrates that provide structural support and anchorage to cells. MMPs are zinc and calcium dependent. Zinc present in the catalytic site is required for enzyme activity, and calcium is not directly required for enzyme activity, but is necessary in the maintenance of proper tertiary structure. 23 types of MMPs exist in humans, which are divided into 6 subgroups based on structure and substrate specificity. So to compare MMP activity between normal and pathological conditions, in normal physiology, MMP activity is intricately balanced at low levels to facilitate wound healing, tissue remodeling, angiogenesis, and other important biological processes that require the controlled degradation and remodeling of the ECM. Under normal conditions, MMP activity is tightly regulated and minimal, as the enzymes are secreted in an inactive state known as a proenzyme and only activated when needed. Versus in pathology, this intricate balance is lost and MMP activity is dysregulated. This causes excessive ECM degradation, which aids diseases like cancer by breaking down the physical barrier of tumor cells and promoting their spread. MMP overactivity has been documented in breast, prostate, lung, colon, gastric, and pancreatic cancers. So because the dysregulation of MMPs has been linked to disease, the search for molecules that modulate or regulate MMP activity is a target of interest in clinical research. Many molecules have been studied and proven as effective MMP inhibitors, or MMPIs, but have failed clinical trials due to toxic side effects and broad spectrum inhibition, which is when the inhibitors are not limited to one MMP, they can inhibit many. And this is a problem because non-specific molecules may unnecessarily over-inhibit MMP activity, because as I said before, our body still needs some level of MMP expression in normal physiology. Also, studies show that some MMPs have anti-tumor effects. Therefore, inhibiting these would be harmful, and we would instead want to activate them. Therefore, a goal of researchers is to discover safe and specific MMP modulators for potential therapeutic use. So that brings me to the modulators studied here, which are catecholamine derivatives, a class of neurotransmitters synthesized in the body that have been shown to regulate tumor angiogenesis through different signaling pathways. These molecules indirectly influence the production and expression of MMPs, which leads to the promotion or inhibition of tumor growth and spread. However, studies on their direct effects on MMPs have yet to be done. Preliminary studies in our lab focus on the direct binding of these catecholamines epinephrine and dopamine against the catalytic site of MMP9, where we found that epinephrine was an allosteric activator while dopamine was an inhibitor. Therefore, our objective in this study was to explore how the direct binding of epinephrine and dopamine affects the enzyme activity of various MMPs to test the specificity of these interactions. The materials that we used first were the enzymes, which were catalytically active forms of MMP 1, 3, 9, 10, and 12 that we got from Enzo Life Sciences, from where we also got the substrate, which was fluorogenic Omni MMP Red. Epinephrine and dopamine we got from Sigma Aldrich, and the buffers we used two. Both of them were 50 millimolar tris HCl at a pH of 7.5, but one of them had 5 millimolars of calcium chloride added and the other one didn't. The reason we used two buffers was because the study showed that catecholamines are metal chelators, which can capture and bind specific metal ions such as zinc, potentially creating chemical reactions that are not desired or not the focus of our studies. So to avoid any side interactions, we removed zinc and calcium from the original buffer in order to make sure that we were only assessing the pure interactions between the catecholamine and the enzyme. And additionally, since we are studying a potential allosteric activator being epinephrine, we removed calcium to see if the activator could bring the protein structure back to a stable and active conformation, a job that is normally done by calcium. So we performed the assays in calcium-free and calcium-containing buffers to observe the power of epinephrine's allosteric enzyme activation. So for the methods, we did fluorescence assays performed in black NBS 96 well plates. The wells contained 0.5 micromolar of substrate and 0.9 units of enzyme. The modulators were serially diluted with final concentrations of epinephrine or dopamine ranging from 0 to 1.4 millimolar. And then finally, buffer was added to bring the net volume of each well to 100 microliters. Then using the Biotech Citation 1 imaging reader, the plates were read at 530 to 25 nanometer excitation and 590 35 nanometer emission for 30 minutes using the Gen 5 microplate reader and imager software. Then upon assay completion, initial rates were calculated in RFU per min and curve fittings were processed using Sigma plot. Then finally, the binding constants were calculated with the following equation seen here. So for the results, for the sake of time, I just highlighted a few enzymes. So for figure 3, we see progress curves depicting the effect of 0.7 millimolars concentration of epinephrine on MMP9 over 10 minutes in both calcium-containing and calcium-free buffer. Enzyme and substrate in the presence of the epinephrine in both buffers exhibited increased rates of fluorescence compared to the respective controls without epinephrine, proving that epinephrine is activating enzyme activity. Then we also ran blanks, which was just epinephrine in buffer without enzyme or substrate, and those had flat rates showing that epinephrine has no activity alone. And then figure 4 shows the absorbance spectra of epinephrine in calcium-containing buffer, which we did because catecholamines have been reported as easily being oxidized in the presence of metals. But here we ensured that they retain their stability throughout the duration of our experiment. So here in figure 5, we see the effect of increasing concentration of epinephrine on MMP9 activity. So before adding enzyme, the activity in buffer with calcium was about 3,000 RFU per min, as you can see over here, while the activity in buffer without calcium was about 1,000, showing how activity decreases threefold when calcium is removed, since it's necessary for maintaining proper tertiary structure. However, as the concentration of epinephrine increased, a higher increase in the initial rates was observed in calcium-free buffer, which is the one with the clear circles, indicating that epinephrine is helping the enzyme adopt a stable conformation and retain activity despite the lack of calcium. Then in figure 6 shows the effect of increasing concentration of epinephrine on MMP3 activity. In this case, a high increase in the initial rates was observed in calcium-containing buffer. This shows that epinephrine is selective for certain enzymes, since it was able to activate MMP9 without calcium, but not MMP3. Then these are the results for dopamine. Figure 7 again shows the progress curves, indicating that dopamine inhibits enzyme activity. And figure 8 shows that dopamine is stable. Figure 9 shows the effect of increasing concentrations of dopamine on MMP3 activity, where here a gradual decrease in the initial rates was observed in both buffers, but more prominent in calcium-free buffer. This could be due to the lack of calcium already reducing enzyme activity due to the loss of tertiary structure. Then in figure 10, we see the effect of increasing concentrations of dopamine on MMP10, where here we interestingly saw an increase in the initial rates in calcium-containing buffer. This activation by dopamine has never been seen before and needs to be explored further. So this is all the data that I obtained. And then to conclude, the data revealed that epinephrine activated MMP1, 3, 10, and 12 best in buffer containing calcium, with the binding constants ranging from 303 to 407 micromolar. Calcium is essential for MMPs to retain their structure. Therefore, better enzyme activity is in calcium-containing buffer is expected and proves that there are no adverse side reactions occurring with the catecholamine. Data also revealed that epinephrine activated MMP9 better in buffer without calcium. Since calcium is missing, this suggests that epinephrine may be binding to MMP9 in a way that maintains the enzyme structure so that it can retain enzyme activity despite the lack of calcium. Then for dopamine, data revealed that it inhibited MMP3 and 9 best in buffer without calcium. and the lack of calcium may be contributing to this decrease. And then dopamine activated MMP10 in buffer containing calcium, which is new, like I said, because preliminary data indicated that dopamine was an inhibitor. So we would do further experimentation to determine the cause of this result, which could possibly be due to structural differences among different MMP types. MMP10 could be interacting with dopamine in a unique way that we have yet to see and understand. So to wrap it up, dysregulation of MMP activity has been linked to various types of cancer, with MMP modulators being sought as therapeutic targets. Since many MMPs have failed clinical trials due to reports of toxic side effects, our findings of naturally occurring MMP modulators, epinephrine and dopamine, provides a safer alternative for drug design, and their interactions with different MMPs should continue to be studied in clinical research. Also, since many MMPIs have failed clinical trials due to broad spectrum inhibition, our discovery of more MMP-specific regulation, such as how epinephrine activated MMP9 stronger than MMP3, is also important. Further investigation of epinephrine and dopamine's interactions with MMPs and finding similar modulators may aid in designing drugs to specifically target overexpressed MMPs while leaving normal ones alone. Thank you.